The last class, the video part 1, discuss about the VM condition. Finally conclude the VM condition. So now we need to find the midpoint voltage by based on some calculations. So we need to find the VM condition. So there is an assumption is here. So whenever the Vin is coming to VM point, that is Vin equal to VM point, that is a midpoint. In the midpoint case, that is called the unity gain line. So whenever the Vin equal to Vout is equal to VM condition, so in that point we cannot predict the Boolean value because the transistor Mn and Mb are in on. So the simultaneously Mn and Mb are going to be on, so we cannot predict the Boolean value. So also we can predict the logic 1 and logic 0 value. So whenever the logic 1 happens, the greater than the point, greater than the VM point, and also logic 0 we can find by the less than the VM point. So Vin is greater than that of VM, that is logic 1. Vin is less than that of VM, that is logic 0. So now we are moving to the calculation of the midpoint voltage. Calculation of midpoint voltage VM. So in the midpoint voltage calculations, first we are making the circuit diagram. So this is our circuit diagram, CMOS inverter. So in the this is the Mn and this is Mb. This is our input voltage. So this is our output voltage. So in order to find the midpoint voltage, first we will assume that Vin is equal to Vout is equal to VM. Our assumption is the Vin is equal to Vout is equal to VM. So I am changing the input is VM. This one is a negative voltage. Also equating the current of two transistors. So in this case the currents are coming from, this one is IDP and this one is IDN. IDP and IDN. So equating the currents, IDN equal to IDP. So then we need to find the saturation condition of the two transistors. Saturation condition of two transistors for the NFET. For the NFET. So saturation voltage Vsat is equal to VGSN, gate source voltage of the NMOS minus threshold voltage of the NMOS transistor. So that is denoting the N. So already we know that this is our gate to source condition. This is the VGSN. So VGSN now is VM. So already defined that VGSN previously is the Vin. So now Vin is defined as VM. So VM minus VTN. So the hint is, your hint is Vin is equal to VM is equal to VGSN. Also Vout is equal to VM is equal to VDSN. So in this next case we need to think about the VTN is positive. So we can predict VDSN is greater than Vsat, that is equal to VM minus VTN. So This is the condition of the saturation of NMOS transistor. NMOS transistor. So now we can think about the PMOS or PFET. So in the PFET, that is denoted by the transistor MB. So in the MB transistor, so thinking about this condition, so we already defined that VSGP because this one is positive and this one is negative. So VSGP. So VSGP, whenever the VM and the Vout is same values, so the VSGP is equal to this voltage, that is VSDP. So we can write VSGP is equal to VSDP. So next one is the equating the current of the NMOS and the PMOS and calculating the value based on the beta, and we can find the midpoint voltage. So recalling the equation for the ID. So there is a equation for ID. So the ID is, our equation ID is beta n by 2 into VM minus VTN the whole square. VM minus VTN the whole square is equal to equating the PMOS drain current, that is IDP. So VDD minus VM minus VTP mode value the whole square. So now we can divide by beta P and taking the square root. So we can write beta n, then equation 2 are cancelled. So divide by beta P. So the equation become beta n by beta P. Then taking the square root. So VM minus VTN, only the square is cancelled because of the root. So beta P by beta P. So this is going to be 1 into VDD minus VM minus VTP the VTP. So now we can write the VM based on this equation. So root beta n by beta P into VM minus root beta n by beta P into VTN that is equal to VDD minus VM minus VTP. So taking the equation, now the VM is equal to VDD minus VTP plus root beta n by beta P into VTN divided by 1 plus root beta n by beta P. 1 plus root beta n by beta P. So this is the equation. So now we can consider the midpoint voltage. VM is equal to VDD minus VTP plus root beta n by beta P into VTN by 1 plus root beta n by beta P. So from this equation we can predict that So the VDD, VTP and VTN, those are the constant values. So we can rewrite this equation by a ratio, that is the change in value is beta values. Beta are the change in values. Why? Because beta is generally is equal to K times W by L. So the K is the processing parameters of the transistor and the W and L are the width and length of the channel or particular transistor. So only one part of the change in or variable part of this VM equation is beta n by beta p is equal to K dash n W by L of n divided by Kp dash n of p. So we already know that Kn dash and Kp dash are set in the processing of the transistor, and the ratio of the FET sizes establish the switching point. Also that it is important to remember that the N and P FETs have different mobility factors with a typical ratio of K dash n by Kp dash is similar to or equal to 2 to 3 depending upon the details of the processing. This fact has significant effect on the choices we take and make in both sizing of individual transistors. So this is the important one for fabrication of CMOS devices, because the NMOS and the PMOS, the conduction levels are different, and the NMOS have high conductivity than the PMOS. So we need to make the ratio between 2 to 3. We need to make the CMOS transistor moderately. Also, we can rewrite the equation of the Kn dash by Kp dash is equal to mu1 divided by mu p. That is the mobility factor, mu in divided by mu p, that is equal to gamma value. So this is denoting the mobility ratio. So also we can make the one note. So the note is the symmetrical condition of the CMOS inverter. Symmetrical condition of the CMOS inverter. So the symmetrical condition of CMOS inverter. There is a note. There is a note. CMOS condition of the symmetrical condition of the CMOS inverter. A symmetrical inverter, the VTC is one that has equal 0 and 1 logic. So in order to make the 0 and 1 logic, the input voltage ranges, we can determine the midpoint voltage VM is equal to 1 by 2 into VDD. So we can recall the IDN and IDP equation. So equating the equation, beta n by p, beta n by 2 VM minus VTN the whole squared is equal to beta p by 2 into VDD minus VM minus VTP the whole square. So we will make the ratio beta n by beta p generally, that is equal to VDD minus VM minus VTP divided by VM minus VTN the whole square. So we can replace the equation by VDD minus 1 by 2 VDD. So VDD, so VM is now is 1 by 2 VDD. So VDD minus 1 by 2 VDD is 1 by 2 VDD only minus VTP. VDD minus VM. So VM now is 1 by 2 VDD. So VDD minus 1 by 2 VDD is 1 by 2 VDD only minus VTP divided by VM is what? VM is 1 by 2 VDD minus VTN the whole square. So one of the important one in the symmetrical condition. So whenever in the symmetrical condition, we can determine the VM is 1 by 2 of the VDD. That means the middle point is set into the middle portion of the power supply. So this allows to compute the transistor size for the particular choice of VM. So always note that the value VTN is same as that of VTP. The threshold voltages are same in the case of symmetrical design, and also beta N is equal to beta P. Therefore, the device transconductance values of two FETs are equal. It is important that beta is proportional to the aspect ratio. So the aspect ratio is W by L. So W is the channel width and the L is the channel length of a MOSFET. And also note that this W by L is the variable parameter in the actual design or the physical design. This is the all about the DC analysis of the CMOS inverter in the electrical cara of the DC characteristics. So we can conclude that in the DC characteristics, so the DC analysis we are performing, in the DC analysis we can determine the logic value, noise margin, and VTC, voltage transfer cara, and also defining the VM point, that is a middle point voltage. Also we can find the VM voltage based on the two currents of the two transistors IDN and IDP by based on the general equation, by based on the beta value. And also in the VM condition, we can determine the one of the variable parameters are the beta N and beta P. So we can take the beta N by beta P in the general equation K into W by L case. So after that we are making the symmetrical case, that is VM is equal to 1 by 2 VDD and taking the ratio beta N by beta P. So generally beta N is equal to beta P. So in the accept ratio condition, we can determine the W by L. So in the actual physical design of the CMOS inverter or any transistor, the variable parameter is the W and L, that is channel width and the channel length. Thank you everyone.